Hi everyone, it's Kira Garfolo with Greenville Tech's Math 120. Today we're going to cover all of Chapter 2. So we're going to cover Chapter 2.1 or Section 2.1, Section 2.2, and Section 2.3. Basically, it's the entire chapter about graphs. So our first section, we're going to be working with qualitative data. So remember, what is qualitative data? Remember that it is categorical data. There's no measuring, there's no counting. It is a quality such as eye color, hair color, model of car, type of class, subject, things like that. And anytime we're dealing with data, especially qualitative data, a good first step is to just determine how many observations are in each category. In other words, all you're going to do is count how many of each group do you have. The formal definition of this is a frequency distribution. So to make a frequency distribution, you guys have all done this before. You just didn't know that's what it was called. You're going to list all the categories, and then you're going to count how many of them line up in each category. You're going to create a table to list the category in the first column and the frequency in the second column. As a good rule of thumb, if you know how many you had to begin with, it would be a really good idea to add all the frequencies up and make sure that they total your sample size. So if you know that you had 30 people and you were separating them based on major, for example, you would certainly want to go back and add all the individual major frequencies and make sure that they totaled up to that 30 that you started with. It's really easy. That sounds really, silly, but it's actually really incredibly easy to miss one or two, and then that'll help you fix that error. So if you were in class, we would be given starbursts and we would do a frequency table with colors. Instead, I'm going to simulate what you would be seeing. And if you remind me in class, I should have some candy and I'll give you the candy anyway. We just won't do the graphs. So what students do is I give you a pack of the two starbursts and you're going to tell me what colors you have. I'll write down the colors and we'll create a frequency distribution. Before we go there, I want to show you what could happen if we had done in StatCrunch. So let's look here. And let's look here in this column right here entitled Starburst, okay? And we're going to say that these are the observations that I took. So let's say that I had 15 people in class, so I have 30 total starbursts, and I recorded each one as we went. Now it'd be easy enough to tally up and write down how many we have in each. But StatCrunch will actually do it for us too. If we go to Stat, Tables, Frequency, we choose the column that we're talking about. So we're talking about Starburst column here. And for now, we just want to ask for the frequency. And we press Compute. Here, we can see that StatCrunch gives us the frequency table. There were 5 oranges, 9 pinks, 8 reds, and 8 yellows. Now, related to frequency is something called relative frequency. So the frequency is just the raw count. How many did we have? But remember, that might not be very useful if you wanted to compare your class with 13 people, for example, to one of my other classes at main campus that has 25 people. Just talking about how many orange starbursts they were wouldn't make sense to compare because there were more people over there. There should be more orange starbursts. So instead, we can talk in terms of relative frequency. In relative frequency, we're going to calculate the proportion, or we can talk about it in terms of percentage of observations that are in that category. So instead of saying, hey, 9 of them were red, we're going to say, hey, 25% of them were red, or whatever those numbers turn out to be. Another self-check is that your relative frequency should add up to 1 if you're using the decimal, or 100% if you're using percentages. Again, it's really easy to lose track of some numbers there. Now, if you're having to round, it's okay if you're off by a teeny tiny bit, but it should be awfully close to 1 or 100% at the end. So we could do this by hand by calculating how many are in each category. So how many reds did we have, and divide by the total number that we had. So I believe that we had, how many did we have? We had 8 reds. So 8 over 30 would be the relative frequency for red. whatever that comes out to be in decimal. If you're asked on a test, you can leave it as 8/30. I'm not going to ask you to simplify it. I'm not going to ask you to put it in decimal form. The homework probably will, and it'll be specific, but if there's no further directions, 8/30 is a perfectly valid example and answer. Now, we can do this in StatCrunch too, using the same steps. If we go to Stat, Tables, Frequency, we're talking about the starbursts. And now, instead of just frequency, we're going to hold down Control or Shift, and we're going to ask it for also relative frequency. You have to hold down that Control or Shift like it tells you to select more than one. And we press Compute. And now we see that we have a new table on our output. We see the frequency right here, so 5, 9, 8, and 8 still, and the relative frequency over here in decimal form. So 0.167, 0.3, 0.267, and 0.267. That is called our relative frequency. Now, a table isn't really a graph, but it gets us towards the right process. Once we've organized our data using these tables, we can construct a graph. Think about it. If I tell you data in a paragraph, I just tell you about it, or I show you a table, or I show you a picture, the picture is going to stick with you the longest. So this is why graphs are important. But we've all seen really terrible graphs in our time, and you have to remember that you need to use graphs responsibly. In section 2.3, we'll talk about ways that we can mislead with graphs, or we can be misled with graphs, and things to watch out for and avoid if you're reading a graph or if you're making a graph. If we're dealing with qualitative data, one of the biggest and most frequently used types of graphs is a bar graph. So in a bar graph, you're going to list your categories on your horizontal axis. You're going to have your frequency, or you can do relative frequency. Be careful on your project because it asks for one or the other on certain problems. On your vertical axis. So how high the bar is how many, and the categories are across the side. And your bars are just rectangles for each category that have that height of frequency. Here, when we're dealing with categorical qualitative data, our bars do not touch. Do not let these bars touch. Now let's make a bar graph with our candy data. You can draw this by hand, or I'm going to show you how to do it in StatCrunch. We're going to use that same data. Pretty much everything else we do today is going to be under graph. So we'll go to graph, and we want a bar plot. Bar plot, bar graph, those are the same things. Now here we have with data. With data means that you have each individual observation. So we knew, hey, pink, pink, red, orange, yellow, so on. We didn't just have, there were 5 yellows, 3 oranges, etc. In that case, if you just know the total counts, you would use with summary. But here we have with data. And our data is in the starburst thing. And there's nothing else that we need to do here at this point. We just say, hey, we're working with starburst data. Give me a bar graph. And here it is. You can see that orange, pink, red, and yellow are on this horizontal axis. And the frequency is the height of the bars. Now, something cool with StatCrunch is you can hover over this bar and it'll tell you what the frequency is. So you don't have to worry about trying to line it up perfectly. And we can see that this agrees with our table. You could draw this just as simply if you weren't using StatCrunch. Okay, now there's something called a Pareto chart. And a Pareto chart is nothing fancy. It's a fancy name for something we've already done. All it is a special type of bar graph. So instead of putting the categories in any order that you want, they have to go from tallest to shortest. So they go from highest frequency to smallest frequency. We can draw this by hand pretty easily, but StatCrunch will do it for us just like it does everything else for us. If we just modify the graph, I'm going to leave this here for comparison. We see that this is the tallest, and then these two, and then this one. So we should see pink and then red or yellow and vice versa, and then orange. So if we go to graph, bar plot with data, and starburst, and we want a Pareto chart, we need to say, hey, we want you to order it. We want you to order it by the count, and we want count descending because we want to go from the largest down to the smallest. Ascending would go the other way. Just as a side note here, in this type, you can also tell it that you want it in relative frequency. So remember I said you could do frequency or relative frequency. That's where you would change that. Okay, so once we have it in count descending, we can say compute, and it's going to give us our Pareto chart. And sure enough, here it is. It's the same data, but you can see that we're always going down, or at least going level. We never go back up like we went here and then up and then down. We don't ever go on the roller coaster. We're only going downhill on a Pareto chart. Now, there are some modifications that you'll commonly see in bar graphs. One of them is to, instead of use vertical bars, so instead of having your rectangles going up, you can have them horizontally, so you can have them laying on their side. Here you would just switch your axes. So now however far right it goes is how many it has. So the right is the frequency. And then your categories are up on that vertical axis. This is commonly used if you have very large category names, because you can think about trying to write a long category name right below a teeny tiny rectangle. It would be kind of difficult. So you can actually put it on its side. You can also have a side-by-side bar graph where you put the bars side by side for categories. That is easy. It allows you to compare two samples, but remember, to meaningfully compare, you must use relative frequency. Otherwise, we're back in that situation where we're comparing a class of 13 people versus a class of 30 people. It doesn't make sense. So always use relative frequency if you're comparing. We also have pie charts. Pie charts are so commonly used, and I hate them. Truth be told, they're my least favorite chart. They're commonly misused, but you'll see them everywhere if you go to a poster session. That's just the way it is. Pie charts can compare relative frequencies for qualitative data. They are most useful for looking at how much of the whole one category takes. Okay, so we're comparing parts to the whole. If we want to compare parts to other parts, it makes the most sense to use a bar graph. It can get really tricky to compare slices if they're barely different. Obviously, if one of them is 50% and one's 25%, that'll be obvious. But what if one's 25% and one's 30%? It gets really tricky. So again, if you just want to see how much of the whole something is taking up, a pie chart can be your answer. But if you're wanting to compare the colors directly to themselves or the other categories directly to themselves, a bar chart's definitely the way to go. Now, pie charts are easy to sketch by hand, but they're actually quite complicated to draw accurate. So unless we're using technology, I'm not going to ask you to draw a pie chart unless it's very obvious percentages. You guys can draw a half of a circle or a quarter of a circle, but I'm not going to be asking you to draw 16.7% of a circle. You would need a compass and a protractor to do it right. And I haven't used those since geometry, so we're not starting today. If we want to make a pie chart with our candy data, we're going to do that in StatCrunch. So we'll go to Graph, Pie Chart, and again, we have our data. It's the starburst, and we don't really need to change anything else. You guys can play around. All these things can make it really pretty, and you can personalize it and all of that. But really, unless you're talking about publishing it or using it for a poster session, just to get an idea for your homework or even for your projects, you're good to go with just the basics. Now this one's fun because the colors obviously aren't going to match the colors of the starburst, so just make sure you read and pay attention. Here we see that pink takes up this slice, it's 30%. Red takes up 26.67, yellow takes up 26.67, and orange takes up the smallest at 16.67. Again, we can see, oh wow, pink takes a good chunk here, but we wouldn't want to compare red and yellow or orange and yellow because it's really hard to quantify how different they actually are. Now that is actually it for the qualitative graphs that we will cover. Make sure that you can do your homework, make sure that you're comfortable with these because you will see them on your project. I would highly encourage you to go ahead and start looking at these types of things on your project especially after we finish here all of chapter 2. You can do a good chunk of the project once we get through there. And I would highly encourage you to go ahead and look so that you can get help if you need it. Now, in section 2.2, we're going to be talking about quantitative data. And in quantitative data, remember that we are dealing with measurable or countable data. So here, we're not really splitting it up into classes, but in the last section, we talked about graphs for that qualitative data. And now we're going to talk about that quantitative data. So just like before, we can start by looking at how many we have and where. If we have a discrete variable, so remember that discrete variables are countable, they're those whole number values, we can actually make a frequency table for each discrete value if only a handful of values are possible. So if you're talking about the number of classes someone is taking this semester, it would make sense to say, okay, 0 or 1 or 2 or 3 or 4 or 5 or maybe 6. Most people aren't taking more than 6 classes. But if you were going to talk about the number of leaves on different trees, you would want to actually do groups of leaves, right? You wouldn't want to say, oh, 100 leaves, 101 leaves, 102. You would maybe make a category for 100 to 199 leaves, and then 200 to 299 leaves, and so on. These are called classes, and we'll see those here more in a second. So after we look at our frequency distribution that we count where each one lies in our classes, we can visually represent it as a histogram. And a histogram is very similar to a bar graph that we just saw, except now instead of dealing with categorical qualitative data, we're talking about quantitative data. So the height of each rectangle is still the frequency or the relative frequency, depending on which way you're doing it. And that's going to give us the height of those bars. In this situation, when we have classes, the width of each bar is going to align with the width of each class. So you're going to use a number line as your horizontal axis. Let's look here at an example. In this example, a random sample of 20 American men aged over 40 has been surveyed, and each of the participants is asked how many marriages they've had. And we see all answers here. So there's 20 numbers here. And if we tally the results, we get that 4 of them were 0, 4 of them were 0, 8 of them were 1, 4 of them were 2, 3 of them were 3, and 1 of them had been married 4 times. So we can construct a frequency table or a relative frequency table over here just the same way we did in the last section. Easy peasy. We can also make a histogram that we'll see here in a moment. I will show you the steps in StatCrunch. And it's going to be just through the graphs histogram section. And we'll see how this works. You can see we did one as a frequency and one as a relative frequency. And here, it's neat because unless you read this here, it's the exact same shape as it should be, as the bar charts are. Remember, frequency and relative frequency should all have the same shapes. Now, continuous data is a little bit different than working with discrete data, because remember, in continuous data, all those decimal and those in-between values are possible. So we can't just talk about the number of something and have a category for every individual observation. Instead, we have to use classes. And each class is going to represent an interval of possible observation values. Okay, so we're going to say, okay, the weight is 0 to 5 pounds, 5 to 10 pounds. Well, I guess 0 to 4.9 pounds, 5 to 5.4 pounds, 5.5 pounds, and so on. Okay, so you're going to go up in categories and they're not going to overlap. The smallest possible value in a class is the lower class limit, and the largest possible value in a class is the upper class limit. So if I have a class that's 100 to 149, the lower class limit is 100 and the upper class limit would be 149. The class width is the difference between consecutive upper limits or consecutive lower limits. You can use either one. Be careful here. So many points are lost on tests. The width of a class is not the same as the upper limit minus the lower limit, okay? And I'm going to show you an example here in a second. It's a good idea to have equal class limits just so that you're not jiggling them around. Sometimes it makes sense to have some classes wider than others, but in general, especially in this course, having equal class limits is smart. It's also possible to have open-ended classes. So you'd have, 21 or fewer on your lower class or 70 and up on your upper class. This is good for things like age or anything that you expect a few stragglers in the end zones, but you don't want to go all the way up there categorically. So if you think about age of runners of a marathon, for example, you may have an age group that is 60 plus, because you wouldn't expect, I'm sure that there's an 80-year-old marathon runner, right? But you would expect only a few to be over 60. So you're going to pull it down and collapse them into one. So let's look at an example here. Suppose we have the following observations for graduation rates. These are 60 US public colleges. So we have N equals 60. And we see we could actually create some classes on our own and count how many are there. But really, that would be kind of tedious. Instead, let's use StatCrunch. Let's look here. We can construct a frequency and relative frequency distribution. This can be tricky to do in StatCrunch. So let's just look at how to do it by hand. We're going to put a class of 20 to 29, and then 30 to 39, 40 to 49, and so on. Nothing is higher than 99, so we'll cut it off up here. We're going to have the lowest class limit is 20, and our class width is actually 10 here, because we have 20 to 29, and then 30 to 39, and 40 to 49, and so on. Remember, I said it's not the upper minus the lower for a single class. That would give us a class width of 9, which is incorrect. Instead, we want to compare these numbers here. So 40 minus 30 is 10. Or you can look at consecutive uppers. 59 minus 49 is 10. I always encourage you to go somewhere in the middle of the table, because sometimes these last ones can be those open-ended endpoints. But if you use the middle, you should always be safe. We could count and see that 3 of them fall here, 9 of them fall here, and so on. And remember the relative frequency, we had 60 total, so 3 divided by 60 is going to give us 0.05. 9 divided by 60 is going to give us 0.15, and so on, just like before. Now, as I was saying, we're going to move over to StatCrunch, and we're going to construct a histogram. I've already loaded this data into StatCrunch right here. In this first column, it's example 1. And I'm just going to go to graph histogram, and I'm talking about example 1. Now, if I don't want to control exactly where the how wide the bars are or anything, StatCrunch is going to automatically do it for me in a reasonable manner. So if I just want to trust StatCrunch, all I have to do is tell it its variable. I'm going to leave it as a frequency histogram. Remember, we could change it to relative frequency just as easily. And I'm going to ask it to compute. And this is what we'll see. So you can see the bars are touching because it's a histogram. And if you hover over, you'll see an interval form. You will see the classes. So this is 20. Remember, that square bracket tells you that 20 is included. And this is 20 all the way up to 30. Remember that rounded parenthesis says that 30 is not included, but everything less than 30 is. So this is 20 up to 30. This one's 30 up to 40, 40 up to 50, and so on. And again, hovering over, we see the frequencies. Makes it a lot easier when we're trying to look out here and say, where does that line up on the axis? It's just a lot simpler for it to say, hey, the frequency here is 6. Now let's say, if we go to options, we can go back and edit it. Let's say that we didn't like the way that it separated our classes, okay? We don't want to do it by 10. We want to start it at 18, and we want to go up by 8 at a time and press compute. And you can see here that it will separate those for us. So just to show you that you do have a lot of control over what those look like. Usually as it does it by itself, it's pretty smart, and it uses an algorithm to determine exactly how many classes there should be and what the width should be and so on. but just in case you want to personalize it, there you go. And just like we saw, here's the frequency histogram. That's the one we created. And if we had chosen relative frequency, we would get this relative frequency histogram as well. Now let's talk about practical histogram making. So we just saw that they're really easy to do in StatCrunch. They're pretty easy to do by hand too. Most of the time you're going to be doing them in StatCrunch in this class. I don't typically ask people to draw very many graphs, and if I do, they're very simple graphs. You can see the detailed instructions in your book for the histogram. I just showed you that. We just walked through it, but you always have your textbook for more examples. And remember, there's no single right way to make a histogram. There are really bad ways to make a histogram. You don't want to have it spread out so thin that all your classes are sparse and short. But you and I could make a histogram, both of them be different, and both of them be entirely and totally correct. Your goal is to organize the data in a clean way that describes the shape of the data. Now, StatCrunch will determine our classes for us, but if you ever find yourself in the position where you need to do it yourself, you're going to want to choose a convenient number below the smallest value or at the smallest value for your lowest class limit. Remember that all of your data has to be between the lowest low class limit and the highest upper class limit. So you want to be sure that you're picking reasonable endpoints here. Generally, between 5 and 20 classes are appropriate. If you have a smaller sample size, you want to have fewer classes. Remember, we don't want them all spread out all over the place. A good rule of thumb for your class width is just to look at the range of your data, so the largest minus the smallest observation, and divide it by how many classes you want. But there are some really complex formulas mathematically to tell us the best way to do this. We don't get into this in this class. It has all kinds of fun logarithms and other things, but just know that StatCrunch is doing that in the background. I'm not ever going to ask you to tell me how many classes you need. I might ask you about the class width, but I'm going to give you the frequency distribution, and you're going to be able to tell me about the class width. You're not going to be calculating anything with this formula. Okay, so now that we're done with histograms, we're also going to talk about stem and leaf plots. So stem and leaf plots are also called stem plots. You may see that in some texts. And the rightmost digit here forms a leaf, while the rest of the number is in the stem. So for example, you could turn 23 into 2 with the line 3, or 34.7 into 34 line 7. For a stem and leaf plot to work, your data has to have the same number of decimal places. If it doesn't, you're going to need to round some or truncate some, or however you need to do that to make sure that they line up. The stem and respective leaves should all be in ascending order, so everything should go from smallest to largest. Your textbook, if you read how it says to do it, it encourages you to make a stem and leaf plot and then go back, put it in order, and make another. I say that's silly and a waste of time. Why don't you put your numbers in smallest to largest order and then make your stem and leaf plot? It'll save you a lot of time. And we also need to include a legend to tell readers which digits are represented. Here, up here, this is hard to tell with no other context if this is 23 or 2.3 or some other number. Same here, this could be 34.7 or 347. It's just hard to tell, so we need to make sure that we include a legend. Let's look at an example here, and I'm actually going to put this on a board. So here's our data, and we arranged them in order from smallest to largest first. I went ahead and did that to save us some time. To make a stem and leaf plot here, we're going to have the tens place be our stem and the ones place be our leaves. So I'm going to bring up our whiteboard. And we are going to see, trying to make it so that I can see the numbers. So arranged in order, we know that we have 60 somethings, 70 somethings, 80 somethings, and 90 somethings. So those are our stems, and then we separate it with that vertical line, and we write one number for each observation. So we have 68, and then we have 75, we have 77, we have 79, we have 80, we have 82, we have 92, we have 96, we have another 96, so we need to be sure that we represent all of them, okay? Just because we wrote a 96 once, the whole point of a stem and leaf plot is to show us how many are in each area. So we want to make sure that each observation has its own space. So we write 6 twice since we have two 96s. And then 97. Now this is almost all that we need. We just need to add the legend. So you could say, okay, here's my legend. And I often use the first one, but you could use any of the observations. You could use a number that's not the observation, whatever you wanted. But here I would just say 6, line 8 gives us 68. And that's it for our stem and leaf plot. That's all we need to do. Now, let's talk about how to do this in StatCrunch. Make sure I'm sharing my full screen. I am. We go back to StatCrunch. And this right here is our stem and leaf data, example 2. So just like before, we're going to go to graph, stem and leaf, and we have example 2. Now, I always say, please don't trim my outliers, and we'll talk about that next week. If you leave it as extreme only, it's probably okay for most examples in our book. But in general, I don't like to cut anything off, so I just leave it alone. Now, if you just change nothing else, it's going to do it automatically pretty much for the way that you're going to want it to do. You could change your leaf unit if you needed to, but none of the examples we're going to do, you'll need to mess with any of those settings. And we'll press compute. Now, this is StatCrunch's stem and leaf plot. Notice it uses colons, which is fine for that vertical line. And here we see the same thing that we drew before. Now, its legend is a little different. It tells you the leaf unit instead of giving you an actual legend. And so it says the leaf unit is the ones place. So in 68, 8 is the ones place. If it says leaf unit equals 0.1, then it would be the tenths place. That would be 6.8 in that case. So just pay attention to the leaf unit if that's all you have. Now, some things about stem and leaf plots. Sometimes we'll have stems that get really long and really crowded. And if you end up in that case, you can split the stems. So you could have, if you had a bunch of 70 somethings, you could have 2 7s vertically. You could have 70 to 74 in the first set and then 75 to 79 in the next set. The trick here is that you have to split all stems. So you can't just split the 70s. You have to split the 60s, the 70s, the 80s, and the 90s in our case. So that's something that you need to weigh your pros and cons. StatCrunch will often split them for you if you have a lot of observations, but if you're making them by hand, just be cognizant that you have to split them all. If you turn your head a little bit, you can still see the shape of the distribution. It's very similar to a sideways histogram. You can still see the shape and skew, which we're going to talk about here in a minute, but it has the added benefit that you can actually see the raw data. In a histogram, remember, we can see how many fall in a certain interval, but we don't know what those values are. In a stem and leaf plot, we can say, hey, that number is 68, not just that there's one number between 60 and 69. So why not always use them, right? Well, one of the big drawbacks is that if you have very large data sets or very diverse data sets, stem and leaf plots get really ugly. They get kind of not overly useful and they're hard to follow. So in that case, you'd probably want to use a histogram. The next type of graph we're going to cover is a lot of people's favorites. And I always like to ask these on tests, hint, hint, because they're super easy to draw. Of course, if you guys take your tests online, I may not ask, but if you're taking something on pen and paper for me, you're always going to see a dot plot. These are a simple way to show frequency and shape of a distribution, but you need to have a discrete variable. You're going to list all of your possible values in order on the horizontal axis, and you're just going to put 1 dot per observation. So let's look at this example data here. Let me get our whiteboard again. Clear it off. Now we see that we have values 1, 2, 3, 4, and 5. So all we do is we draw a line and we say, okay, here's 1, 2, 3, 4, and 5. And then we go through and just put dots. So we have a 3, we have a 2 and a 2. These dots are terrible on here, please forgive me. A 1, a 1, a 1, a 5, a 3, a 4, a 3, a 4, a 2, a 1, 2, 2, and 5. Now, if you look at that, you can kind of see the shape here of the distribution, right? That is our dot plot. That's all that we have to do. But if you want to compare it here, think about it. It kind of looks like a histogram, right? We can still see where that data is or the general shape of that data. Lots of things that we can see with just those dots. Super easy to create, super easy in StatCrunch too. Pull us back to the screen. Let's show you in StatCrunch. By now you should know that we're going to end up going to graph and we're going to choose dot plot. This is example 3. And I think actually, before I do this, I need to make sure that my data is correct. I hit my keyboard when I loaded this, so there's a chance that it's not right. Let's take a look at it and see. Let's see if that looks like what we had before. It looks pretty close, right? So you have a dot for every observation. Now I keep talking about the shape of distributions and the skew of distributions. And this is extremely important as we continue through our course. We have lots of different shapes that are possible, but only a few of them are going to be really important for us. So first we have symmetric and bell-shaped. You'll come to find in Unit 3 that this is really a desirable shape for us, okay? So it's bell-shaped, it's symmetric. Symmetric just means that if we split it down the middle, they're mirror images of each other. And a bell shape, you've probably all heard of the normal curve. We'll work with that next unit. But it has that nice bell shape. It goes up in the middle and down at the ends. Another symmetric is the uniform distribution. But instead of being bell-shaped, the uniform, sure, if we cut it in half, it's equal on both sides, but it's just straight and flat, straight across. We'll talk about that in the next unit also. Now, the really important ones for us are skewed. If we're not talking about symmetric, especially symmetric bell-shaped, the skewed distributions are important. So we have skewed right and we have skewed left. Now, the important thing about skew is where the tail is pulling. It's not where the majority of the data is. It's not where it's tallest here. It's where that tail is being yanked towards. So this one is skewed right because our tail is pulling to the right. This one down here is skewed left because the tail is pulling to the left. So always pay attention to where the tail is. Now, I've thrown these other couple of shapes in here. They're not ones that we work with in our course, but know that you can have, they're called bimodal or multimodal, and they are the camel humps. So this one at the bottom is symmetric because they're roughly the same height and they're roughly split in half. And this one's non-symmetric because one is shorter than the other. Now, obviously, these are perfect cases, these symmetric examples and skewed examples. Sometimes our data isn't quite that clean, so we need to just look and see, oh, is that symmetric enough? Or, oh, is that tail pulling enough to be skewed? Things like that. One of the ways that people seem to remember skew is skews with kangaroos. It's silly, but it works for a lot of people, so I wanted to share it. If you're looking at your chart and you're able to place a kangaroo sitting on top of it on your histogram, the way that the tail is the way that it's skewed. So the way that its rear is facing is the skew. So if you look at these underlying charts, you could draw it up here and then it pulls way out to the right. So we put the kangaroo's tail on the right and it's a right skew. Here we pull way out here to the left and then we go up all at once on the right and down. So since that tail is pulling to the left, we say that it is skewed left. Now there's one more plot that our text talks about. I'm not going to spend a lot of time on it. StatCrunch can make them, but it does a lot of other complicated things with time series, so I'm not going to ask you to make any of these. But you see these a lot in daily life, so it's worth mentioning. We can have a time series graph if we plot time on that horizontal axis and whatever we're observing on the vertical axis. Then you just connect each point. So you're not drawing a line of best fit, you're just drawing a really ugly, you can think about things like the stock market or things like that, where it comes up a lot in business. There are actual entire courses. If you find yourself in econometrics at some point, those of you that are in business, you'll see a lot of these graphs. Okay, take a deep breath, pause if you need to. We're about to head into our last section, which is 2.3, which is misleading graphs. This is kind of a fun section because you get to talk about how you could lie or how people lie to you. And hopefully you'll walk away knowing how to look at some things a little more closely when you're looking in media, especially social media, to see how things actually compare. So misleading graphs are everywhere, right? Graphs are really quick and easy, but they're really easy to lie with too. So you want to make sure that you're not lying to your readers if you're making the graph. And just as importantly, you want to make sure that they're not lying to you when you're flipping through the news. So some general things that you want to watch for and avoid if you're making graphs are unlabeled axes. You always want your axes to be labeled so you know what you're looking at. If they truncate, so they cut off one of the axes, or they don't scale it evenly, so it starts by going up by 10s and then it starts going up by 50s, for example, that's a problem. 3D graphs are often difficult. Sometimes you can have a little bit of 3D effect and not cause a lot of grief, but sometimes when they get out of control, they are really hard to read. Sometimes you'll see cute but unfunctional designs. That happens a lot in media, sometimes social media, sometimes magazines. They had a cute idea, but they just didn't go very well on it. If somebody's using different designs throughout the same graph, so maybe they change colors or maybe one bar is a certain different design than others, you want to make sure that you take a minute and figure out why. Sometimes there's a perfectly good reason to highlight one of the bars, like maybe you're talking about different states and South Carolina is highlighted because that's where we're talking about. But also sometimes a difference in design, different in shape, different in color, things like that, might be trying to lead your eye to or away from something specific. So in general, you just want to be careful. Same thing goes with clutter or excessive white space. You want to make sure that your graph is organized and easy to look at. It shouldn't be a whole bunch of empty space with short little bars everywhere. And it also shouldn't be a million things stacked into one place that make it difficult to piece apart. You also want to make sure there's a data reference somewhere. It's important to note that if you're reading an article, it's very likely that you're not going to see the data source directly on that graph, and that's okay. But the data source should be made available somewhere. In the original article, in a footnote, in the caption, somewhere you should know where that data came from, and that somebody's not just making it up. Let's look at some examples, because that's definitely the best way to learn this. Here's an example. These are super common in the stock market. And if you look here, it looks pretty drastic for Tesla this day, doesn't it? You see that it started up here and then, wow, it just plummeted. And you'd think at a first glance, if you weren't used to looking at stock graphs, that if you owned Tesla, it was all up in smoke and you were having a really bad day. But really, that's not fully what's happening here. The axis only goes from 690 to 810. So this whole dip here only goes from about 750 down to about 695. So it's not that huge of a dip. It is a bad, it is a problem. And there's a reason that stock graphs often show what's going on here. because a lot of investors want to see all of that up and down jiggling around because it's important. And to people who hold a lot of the stock, this drop would be significant. But you need to make sure that before you have a panic attack, that you look and see what is my axis and what am I actually comparing. The added benefit here is it's in 3D. Doesn't distract it too terribly much, but it does make it a little more difficult to see. Just a solid line would have been a better approach. You can see this whole tank that looks like 100% down to zero and burning is actually only down about 11% or 86 points. Now, this example came from a magazine or a publication in Argentina, and it was at the very start of the COVID crisis, and this was talking about tests per million citizens. So remember that when COVID first started, it was really hard to get tests, right? Governments weren't supplying tests, we couldn't get them. It was, not very many citizens were being tested, so it was really hard to know how many people were actually sick. So here we see that Brazil was testing 258 per million. Argentina is testing 330 per million. United States is 7,000 per million. Italy is 14,000, and so on. Yep. I apologize, guys. I had to step away for a minute. My child is apparently sick at school. So I'm not sure exactly where I left off. So I'm going to start over on this slide, and I apologize for any inconvenience. So here we have Brazil at 258. Here we have Argentina at 330. You can see that it's a different color, which is something I said to watch out for. Not a big deal here because we're talking about Argentina and they're pointing it out. So no big deal. They want to draw attention to it, and that makes sense. Then the United States is at 7,000. Italy's at 14,000, and so on. Now, do you see the problem here? You should notice that 258 to 330 goes here, and then 330 to 7,000 is the same amount of distance here. And then 7,000 to 14,000 is the same amount of distance again. That is a problem. 14,100, to be fair, should be taller than twice of this. And 330 would look very, very small relative to 7,000. There's no axis here. We always want to look for an axis, and we always want to be sure that they're judged on the same axis. Now, this graph is just a nightmare. Remember, I told you that 3D can look rough at times. I'm not sure what this is, but it's a real graph. I don't remember where it came from. But imagine trying to read this. Those 3D platforms make it really hard to tell what the height actually is. They're stacked in front of each other. There's shadowing going on. It's really just kind of a hot mess. Remember, we could do the side-by-side bar charts. That would be a better way to do this. You could have just straight bars in 3 different colors across the categories. There are probably some other innovative ways to do it too. We also have this example. You guys won't be assigned this assignment, but in the past I have assigned into other sections, that's why it's still here, I have assigned that you need to find a misleading graph in the real world. Again, I'm not going to do that to you guys, but do keep your eyes open because that's something useful to see. But USA Today and other similar publications are notoriously horrible at making graphs. They're cute, but they're not very functional. If you don't believe me, just Google USA Today graph or USA Today bad graph, and you'll see lots of funny examples. This one we see, the hands are holding the world and the sleeves are the rectangles. So where is supposed to be the graph? Is it supposed to be the rectangle or is it supposed to be the height of the hand? As a statistician, I'd look at this and think, oh, the rectangle. But if we look over here at local community for men, there's not even a bar and it's 22%. So it's really kind of hard to see here. I assume it's the hand, but it's hard to see. Are we talking about the tip of the fingertip? What are we talking about? They would have been better to just use bars here and use a cute background or do something else innovative to make it make sense.